So, yeah, in the previous class, we're able to understand the principles of associative memory. Let us say when some information, or let us say a photo is given to you, you are trying to remember the previous past, and we learned how actually this memory is going to happen within the system. Okay, so okay, and we know that the pre-synaptic dynamics, that is pre and post synaptic activities, are very important in order to train a neuron such that it will become, it will learn whatever the previous neuron and the next neuron has learned, and this way multiple neurons get trained. That is, that neurons in between the neurons which were already trained will also get trained, and that form that leads to a powerful associative memory, okay, that relate with one another. Okay, so how do you actually understand this one in terms of mathematics? The dynamics of the system, you can visualize it by imagining a surface of undulating energy. Surface means, undulating means a sinusoidally varying surface. Assume that you have a sinusoidally varying surface with some ups and downs, and which are generated from Lyapunov function. Lyapunov function is written in order to evaluate or estimate the stability of a system. How stable is your system? Let us consider in a surface which is perhaps varying sinusoidally by using Lyapunov's function. In neural network way, the state of network maps to a point on a Lyapunov's energy surface such that which forms the minimum. What are the states of the Lyapunov's energy surface? So, a surface which is varying sinusoidally, there will be many minimums and many maximums. Here, our attractor neural networks falls onto the energy state that represents the closest local minimum under the influence of vector field. What is the meaning is, suppose that you have a small ball and you put on this sinusoidally varying surface. What actually the ball will do? So it is on the top. Now it will settle down to the local minimum. Is it the settling of a ball at a minimum does not necessarily mean that there are no other minimums. Okay, there may be many other minimums which are at a level which is lower than this minimum. However, given the present situation, what the ball will do, it will find a stable state which is the minimum of that surface. So there are many such minimums in this one because the surface is varying sinusoidally. Any doubt here? Yeah, Jatin, any doubt?
No, sir.
Are you able to follow?
Yes, sir.
Okay, see here. Once a network settle down to a particular state, which is the local minimum of that one, of the particular surface, we say that that structure or that connection has achieved a minimum, and that minimum is known as a memory. Okay, so the vector field is characterized by structure of connections, the weights and signal function, where actually the network will go, how actually your network will find the minimum. Network keeps changing from one point to another point, and each time it is going to find a value where is the minimum. Whether the present minimum is more than the previous minimum, yes, then it will continue. If present minimum is only less than the previous minimum, the network is going to stop. So ultimately, if there are, let us say, the ball keeps coming down, every second it comes down because the minimum is not yet found. Once the minimum surface has been found, the ball will not go to another minimum. Just like that, our network evolve in time such that a local minimum is reached, after which the state stop evolving further. Once the ball finds the minimum, it will not go once again to find next minimum, because you will have immediate maximum. So it will settle down at the immediate minimum. So our aim is to find how many such minimums are there in such undulating surface. Okay, so you are saying so much, but what computation you are going to do? That is a very important thing. The computation of a neural network, which is an attractive neural network, the point of local minimum at which the network state stabilizes is to be interpreted as the memory of the system. So we said system has an associative memory. We can remember the past. What is past is a group of the points which have achieved the local minimums. The surface may be very large. There may be 100 minimums. So each minimum may be more than or less than the previous minimum. We are not interested to know whether it is a global minimum or such. What is my interest is within a given surface, within a given dimension, whether this surface is a minimum. Okay, once I found such minimum, I will assume that is a memory of the system. So if I could find many such points, I will assume that all these points will perform the memory. So an input vector sets the initial state of the network. Suppose that the surface is sinusoidal, I'm set at the top. So the whatever I'm rolling the ball at the top, that sets the initial state, which is represented by a point on the energy surface. So it's like a point on the energy surface. The network state continuously changes in the time till the system hits the local energy minimum. So I have released the ball at a place such that energy is maximum. Now my network keeps modifying such that at one point of a time it reaches the local minimum. I'm stressing the word local minimum because it may not be global minimum, and I don't need the global minimum also, because there are many minimums. Each minimum is a memory. Okay, this final state is recalled as a memory vector. Okay, so there may be, let us say, 100 points you have found which are minimums for that surface. Those all 100 points will become memory of the system. The minimum energy points of the Lyapunov function have to be mapped to desired memory states. Okay, so there are, let us say, 100 memory points you want to organize. Okay, memory 1, memory 2, memory 3. So you have found, let's say, many memory points. Which memory points will point to which memory state mapping must be done? This mapping, once you do, that will form the total memory in the system. Okay, any doubt here? Any of you? Huh. Are you able to follow whatever I am teaching? Any doubt? Hmm? Anybody? Are you able to understand what I'm doing?
Yes, sir.
Huh. Now, let us look into associative memory model. How do you model an associative memory? So there is a space which is known as input vector space here, and there is an associative memory block, and there is an output memory space. So input memory space, there is my output memory space, and associative memory. What actually associative memory is doing? Associative memory is basically mapping a vector from input space to the output space. Okay, so associative memory basic purpose is only mapping from either you map 1 to 1 or 1 to 2 or 1 to many or many to 1 is the network designer. Okay, how the network is designed. But basic problem in the associative memory is how do you map a vector from the input space to vector from the output space. Okay, so the memory learns the underlying association from training data set. Why you should train it? You should train the memory such that what input will get mapped to what output. Okay, let us say input 1 maps to output 4, input 5 maps to output 3, or input 6 maps to output 1, like this. How you have mapped an input space into output space is the job of associative memory. That is why we train it. Okay, so whatever model you are considered here, let us say we are designing a neural network. Here you have no control over the weights because of the initial training, the weights have been already programmed. The network is already designed. Then what is your job? Your job is to determine what is the relation between input and output. That is, if you give certain input, because of these weight structures, which one of the output space is mapped to this input system. Okay, that is to be properly encoded in the system. One simple analogy I'll give you. Do one thing. All of you just participate in this discussion so that it can be clear, very clearly understand. Suppose I tell you a song. Okay, one line of the song. What information comes to you in mind? Yeah, all of you participate in this discussion so that it will be very clear for me to understand, tell you this discussion. What information that comes to you? Suppose if I tell that line of song, what all you can tell me about that? Quick. What information you can give about a particular song? Yeah, all of you. Tell me what information you can give me about the song. Suppose I tell you one line of a song. What information you can give? Anybody? You would have seen so many movies now. Then what information you are giving about the song? Anybody? You don't have any information to share? So, what information you are going to share is the, let us say, who has acted in the movie, let us say when you have seen the movie or which movie the song is been. So such information about the song you can give, but those all information are related to that song only, so that what all the information about the song was already stored in you, and now you are mapping those informations to the recently heard song. That is what your associative memory will do. Okay, mapping of the information which were already stored in the input space to the output space, which was actually a song. Now, that's what is told in the matrix associative memory. AI, BI, let us say mapping from input to the output from 1 is equal to Q. There will be Q iterations. AI belongs to the input space and BI belongs to the output space. This I will map it as a matrix A1, B1, A2, B2, so on up to AQ, BQ. A is the input space and B is the output space in kth iteration. So when A is belongs to one space and B belongs to another space, then it is called as heteroassociative memory. For example, A1 to B2, A5 to B6, something like that, which associates two different vectors with each other. So one vector you are associating with another vector. If AI, new AI is equal to old AI plus which belongs to Bn, that is a network which associates old memories to itself, then it is known as auto-associative memory. Hetero-associative memories associate a vector from one space to another space. The auto-associative memory associates the vector within the same space. That's a fundamental difference between these two sort of vectors. Okay, are you able to follow? Any doubt till now? Any doubt? Any doubt till now?
No, sir, no doubts.
Why? Not able to understand? Now, what we
ಏನೋ
do?
ಹೇಳಿದ್ರ ಸರ್ ಕೇಳಿಸ್ಲಿಲ್ಲ.
No, are you able to understand what I'm telling?
Yes, sir, we are following, sir.
Okay. Now, what I'm doing in two memory is I will consider an input vector which has some neurons, and there is an output vector which has some other neurons. I'm mapping from input vector to output vector. It may not be A1 to A1 and A2 to B2. I may map from A1 to B5, A2 to B6, or A3 to B1 or A3 to B3, B4, like that. Anyway, mapping is done. So let us say I may map only first three of this one to all five and the last two of this one to only two. Like this I can have. So I can map the input vector to the output vector if they're in different space, then it become heteroassociative memory. That's what I'm showing you here. So the memory of these vectors that are to be associated is stored in the connection of the network. How I should associate this particular neuron with this particular neuron is stored in the weight vectors. So all the neurons will not get connected to all the output neurons. That is a very important thing. This is completely different from the previous section where connection was there from all input to all output. It is not the case. Some of inputs will get some of the output vectors. Out of one of them may be connected to 10 vectors, but second one may connected to only one vector. How an input gets mapped to the output is already programmed in the network. That is, the programming of weights is done through the number of iterations. Okay, so if there are n number of neurons here and there are m number of neurons at the output, that whole connection will result in n cross m connection matrix. That is W, total connection matrix, which will give you the weights. So B is equal to total output from this one vector is equal to A transpose into W. Why A transpose is taken? Because A is also a row vector and B is also a row vector. W is also row vector. Two row vectors cannot be multiplied. Therefore, convert one of them to column vector. That will give you A transpose W. What is A is the input vector A. W is the vector vectors which are associated weights which are associated with the neural network. Once you do it, if at all you want to introduce additional complexity, then the output can be made some function of A transpose W. For example, whatever outputs you are going to get, that will be multiplied by certain constants. Those constants are declared by certain functions. For example, add 1.2 or some 0.3 to each one of them or multiply by certain value at the output. This can be done so that the output will be mapped to input properly. Okay, is it clear to you? Now, we will look into Hebb association matrix. First, let us understand what is Hebb's postulate. A Hebb's postulate simply states that the change in the synaptic efficacy means whatever you know, you are training the other. So, what actually says that a neuron knows already something. That neuron is trying to train another neuron, means it is trying to teach another neuron whatever it has already learned. So how much it can teach, that is proportional to the product of presynaptic and postsynaptic neuron signals. Are you able to understand this one? Any doubt here? Anybody can tell what is the meaning?
No, sir.
Any doubt? Any doubt?
No, sir.
See here, we tell that neuron will understand something only when it is trained such that the postsynaptic, that is after the neuron and before the neuron, the energy or information whatever is carried is very high. So only when the neuron will get trained. That's what is said. It is proportional to the product of pre and post synaptic neuron signals. So how do you formulate this principle? Let us consider two layers, Lx and Ly, and we know that all input vectors are connected to the output vectors, and all output vectors are in some way connected to the input vectors by a connection matrix. This connects the weight vectors, how they are formed, 1 to 1 or 1 to 3, 1 to 4, are formed according to the relation delta Wij is equal to n, eta is the learning rate, ai any one of the input vector, bj is any one of the output vector, a1 to b2 or a3 to b1, something like that. So these two layers, one of them has n inputs and another one has m outputs. So n cross m neurons you have totally. So that this is a total connection matrix. So total is input, some outputs are there that are coming and joining the inputs. From these inputs, the vectors are going for outputs. So it is inputs to output as well as output to input connection. So actually, when you have this one, I'll tell A is equal to A1, A2, A3, An, so on. These are all the training vectors, that is input vectors, which are given to the network. And B, B1 to Bm, that is output produced by the output vector. Now what happens when eta is equal to 1, that is learning rate is equal to 1, I'll multiply these two, that is A transpose, A into B transpose I will do. So that will give me A1, A2, A3 in this vertical manner, and B1, B2, B3 in the horizontal manner. So A1, B1, A1, B2, A1, B3, so on up to A1, Bm. Similarly, A2, B1, A2, B2, so on up to A2, Bm. Similarly, all of them you will get this matrix you are going to get. This is nothing but AB transpose, because otherwise these two matrices could not be multiplied. Now, when you understand this weight vector, let us understand what is the meaning of linear associative memory. So once you have encoded a matrix A and B with n inputs and m outputs, now I'll assume that W is equal to AB transpose, which we derived in the previous section. Now B dash is nothing but B transpose only. B transpose is nothing but B itself. B is equal to A transpose W. This equation I am getting from here. B is equal to A transpose W. I am using the same equation here. So this is equal to A transpose. But what is W? A into B transpose. When I multiply A transpose into A, I'm going to get A square. Okay, A transpose A is A square into B transpose. Once I have B is equal to A square into B transpose, suppose there are Q associations, that is in the training set, there are Q number of trainings you have done, iterations you have done, that has to be encoded, so the encoded such that input will be correctly encoded into output. The resulting matrix is equal to W is equal to AK into BK transpose. Both of them are the vectors which have n number of entries. So before we proceed, one very important thing you have to understand is the vectors which inputs are given A1, A2, A3 are to be orthonormal and orthogonal to each other. Anybody, what is the meaning of orthogonal vectors from mathematics? Yeah, anybody, what is orthogonal vectors? Are you able to hear me? What is orthogonal vector? Any of you? What is the meaning of orthogonal vectors? Sharanya, Chandan, what is orthogonal vectors? Huh? Yes, perpendicular vectors. Two vectors are said to be orthogonal if they are perpendicular to each other. What is orthonormal? Orthonormal means all the vectors are normalized, means their magnitude is 1. So a vector is divided by its magnitude. Once you divide a vector by its magnitude, the resultant vector will become a unit vector whose magnitude is equal to 1. Two conditions must be satisfied. The vectors are orthonormal also, and also they must be orthogonal to each other. So each vector A1 is perpendicular to A2, A1 is perpendicular to A3, and A2 is perpendicular to A3. So like that, all the vectors are orthogonal to all other vectors. Once they have the unity magnitude also, in such a case, the association A is presented to neuron in the layer X, then B dash transpose, that is AI transpose into W, is equal to AI transpose into, what is your W? K is equal to 1 to Q, AK, BK transpose. Now, yes, Chandan, correct. Now, when I is equal to, let us remove only the vector I, AI, BI transpose, I'll take it out. It involves all of them except K is not equal to I. K equal to 1, 2, 3, everything is available except K is not equal to I. AI transpose into AK, BK transpose. Are you able to follow? Only AI, BI transpose are taken outside, remaining all are grouped into something. Now, if two vectors are orthogonal to each other, their multiplication or dot product will become 0. That is, A dot B will become 0. Why are taking dot product? Because the dot product represents a matrix multiplication. So A transpose AK represents matrix multiplication or dot product of two vectors which are orthogonal. So any two vectors which are orthogonal, the dot product of this one is 0 because angle between them is 90 degree. AB cos theta, theta is 90 degree, A into B into 0, that will give you 0. So entire term will become 0, that will be cancelled. So remaining term I have AI transpose into AI into BI transpose, that is nothing but equal to AI square into B transpose. But what is AI square? AI is a vector which is orthonormal. That is, magnitude of AI is 1. Therefore, 1 square is equal to 1 only. So ultimately, you are going to have only BI transpose. So these associative memories are called as orthogonal linear associative memories. We choose the memories or input vectors such that which are orthonormal and also orthogonal, such that the final result will become only linear. Now, once you understand the principle of orthogonal vectors, now we'll get into half-filled network. A half-filled network is nothing but it is a recurrent single layer neural network. It's a recurrent single layer neural network which are essentially dynamic systems that feed the signal back to them. That is, signal is fed from A to B. In turn, the signal is fed from output space to input space. And also, some signals are fed within the system. That is, if you have an input space, some signals are fed within the same signal space. That those sort of networks are known as half-field networks. Okay, then these models possess a rich class of dynamics characterized by existence of several stable states. So these models have many stable states. Okay, so some models have only one stable state, some models have many model states. We choose a half-field network which are having self-mapping ability because they have many stable states. Okay, and what we do, what is the use of those stable states? Those stable states are mapped to certain memory vectors. So whatever the stable states of these networks, they are mapped to desired memory vectors. Suppose that as I told you, when I tell you a song, you will be able to remember some specific features of the song, who has sung the song, which movie it was, and who was acted in that movie. All those information are related to that song only. You don't remember some other actor or some other situation which is not related to the song. What actually you should understand is, when an input is given, you should remember the things which are associated with that input only. That is very important. There actually the half-field network is going to be very important. Okay, now, you said that these outputs of the network corresponds to the memory. Ultimately, our aim is to find such a set of points which will act as a memory. These memory, what is the use of this memory? I will tell. These memories are associated with that vector. Understood? Any doubt here? Are you able to follow? Now, how do you form the half-filled networks? A half-filled network is a self-associative memory. See here, there were many inputs, I1, I2, I3, so on up to this much. There are many connections of one to, let us say, this to this one only, A to B, A to C, A to D. Similarly, D to B, D to D, D to A, something like that. So the weight vectors are associated with each one. So self-association W1I, W if I is equal to 1, then it is self-association. W12, that is what is the association of 1 with 2. W13, it is what is the association of 1 with 3. So W1L is what is the association of vector 1 with vector L. Similarly, same thing will happen to what is the association of 2 with 1, 2 with 3, 2 with 4, or 2 with 2, something like that. So it is a self-association recurrent network. And how do you, what is the mathematical equation which governs such networks? It is equal to xi dot is equal to minus ei xi. This is a passive decay, and a summation j equal to 1 to n wji. It's a weight vector which we have designed in, we have gone in the previous section, w11 to w1n, wn1 to wnn. So it is a n cross m structure. Okay, and delta j of xj, that is whatever is input is given, finally that will multiplied by certain weight factor wij, and ii is an external input. This output you are going to associate with some external input. Okay, where the individual neurons can have distinct sigmoidal characteristics. The neurons, whatever you have, 1, 2, 3, 4, so on up to n, they are not linear neurons. They have sigmoidal characteristics. Any neuron which is sigmoidally characteristics will have something like 1 minus e power minus lambda ix divided by 1 plus e power minus lambda ix. So what is the which is this function is specifically chosen such that inverse of this function is such that 1 by lambda into ln of 1 plus s by 1 minus s. That is what is s actually, where s is equal to 1 minus e power minus x by 1 minus 1 plus e power minus x. The functions of the neurons are such that they follow sigmoidal behavior and they are self-associative in nature. And this is done with trial and error, so that my inverse function should follow this one. So basically, when it's calculated, inverse is found. As long as it does not satisfy this condition, once again I keep varying. So once I know that my both the equations, the direct and inverse satisfy certain conditions, I'm going to write a function for neuron. Okay. So your signal function is like this: minus 1 to plus 1, maximum variation si of x, this one. Okay, by varying certain values for x. Okay, it is e power minus x. Therefore, if you vary large point at one point of the time, it is going to get a maximum value. Okay, next what happens? Inverse of bipolar sigmoidal function. Whatever bipolar sigmoidal function is, it is at some point it is starts from minus 1, ends at plus 1, at middle point it will become 0. The inverse of this one is, let us say, it is from minus, starts from certain value minus 5 and ends, it goes to larger values because I have shown a peak at this point. Okay, this is how actually the plot will go on, the signal function and its inverse. Okay, so this system represents a high dimensional cross coupled non-linear system, which it becomes very difficult to analyze how to find a closed form solution. Okay, so it is difficult to find the closed form solution. Let us, you have to make certain approximation, which will give me certain sets of answers. Okay, any doubt till now? Are you able to follow?
Yes, sir.
Okay, so we'll stop the class now. Okay.